Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Nuridani binti Sulaiman, and I would like to present about the introduction for the assignment. So, for a control system, it is a system with an interconnection of components forming a system configuration that provide a desired system response. Basically, there are two basic categories of control system, which is an open loop system and a closed loop system. An open loop system, the output of the system has no effect on the control action, and for a closed loop system, it utilizes an additional measure of the actual output to compare with the desired output response. So this is our question for the assignment. In this assignment, we need to design a closed loop system, PI and PD and PID controller that are need to be designed and analyze the system performance related to the each of controller. For a closed loop system, the signal is fed to the controller to reduce the error and bring the output of the system to a desired value. A closed loop system, also known as a feedback control system. A proportional integral derivative controller, which is a PID controller, it is a closed loop system which generally with a single input and single output (SISO). PID control handles the step changes to the set point especially well with a fast rise times, little or not overshoot, fast settling times, and zero steady state error. So this is the function of P, I, and D in PID controller. P stands for proportional terms, which is a present element. To speed up the closed loop response, the proportional terms minimize but does not eliminate the steady state error or offset. I stands for the integral terms, which is a pass element. It is to eliminate the offset or steady state error. This term also speed up the system response but at cost of sustained oscillation. The last one is D in PID controller, which is a derivative term, it is a feature element, and the introduction of the derivative action means that changes in the desired value may be anticipated, and thus an appropriate correction may be added prior to the actual change.
So we continue to the mathematical model derivation. This is all the info that we get from the question, which is J is 0.01 kg per meter square, B equal to 0.1 nanometer second, K equal to 0.01 V per rad per second, KT equal to 0.01 nanometer per ampere, R equal to 1 ohm, L equal to 0.5 Henry, N1 equal to 10, and N2 equal to 1000. Resistive transducer coefficient equal to 0.1 ohm. So this is all the equation that we all got. This is the first equation, the second equation, third equation, and fourth equation. After substitute 2 and 3 into 1, we will get the fifth equation. And after substitute the equation 4 to equation 5, we will get the final equation, which is this. Theta per m will be the output and VA will be the input. So I will continue to the width year calculation. We got JEQ equal to J plus JL and 1 over N2 power of 2. And DEQ will be B plus BL and 1 N per N2 power of 2. And After we key in all the information that we get from the question, we will get this, and after simplify, the answer will be this. We can use calculator to solve this equation. So after we get the final form of equation, we can use this kind of method to find B1 and C1 to declare this system is stable or unstable, because all elements in the first column have the same sign and all the roots are in the left hand of the S-plane. Therefore, the system is stable. So the system is stable. That's all.
Okay, my name is Ifazlaika binti Saiful Bahri and my metric number is 8E170131. Today I'm going to talk about the MATLAB code that we are using for this to solve the problem. So we insert num, which is numerator, which is based on the calculation, manual calculation, we got 200. And then we got denominator, 1 is equivalent to s cubed, 12.2 s squared, 222s, and 0 for. And then I set t here, which is the transfer function. H equals to 1 for the feedback. M is equals to feedback t and h, which is forward path function transfer in h as feedback, and t over 1 plus t times h, which is the formula for closed loop. So I set step m for the step response for m. I wrote here hold on because I'm going to show you the graph later on. Then in the next command, I'm going to show you the system, the PID system, which we can change the variable here. So KP is equals to 1. Like I can change this value, any value that I want. So Kp is equals to 1 for the P system, Ki is equals to 1 for the I system, and Kd is equals to 0 for the D system. So Kp and Ki equals to 1 means it is Pi system. Then Gc equals to PID, Kp, Ki, Kd, this is the PID controller. Then I'm going to set another function, transfer function, which is MC equals to feedback GC times T and H. This is the closed loop transfer function G over 1 plus GH, but I'm going to set G as controller in forward path. Then I'm going to set step MC, which is the step response for MC. Then I'm going to put grid on. Then I'm going to run this to look for the step response. So this is for the KP and KI, which is the PI system. So the PI system is to eliminate the steady state error from the P controller. Actually, I have to show you the P controller first. So here I'm going to set it as 0. And I'm going to run it. And this is the P only controller. So the graph is like this. This is like the critically damped graph. And then, like I've showed you earlier, the PI system I'm going to set I as 1, and then I'm going to run it. So it shows that PI system is under them. The PI system eliminates steady state error from P controller. And then I'm gonna set I'm going to show you the PD system. So I'm going to set I as 0 and D as 1. And then I'm going to run it. It shows that this is continuous time PD controller in parallel form. So this is the graph. The PD is to increase stability of system by improving control, since it has the ability to predict future error of system response. And then I'm gonna show you the PID system. So I'm going to set I as 1. I'm going to run this. So this shows that this is the PID controller in parallel form. So the step response shows that this is the graph for the step response. PID has the optimum control dynamics, including zero steady state error. PID can be used with higher order processes, including more than single energy stored. That is all for me. Thank you.
As a conclusion, despite all the odds and difficulty, finally this project objective was achieved, and all the theories were applied, and we used MATLAB in order to identify the value of P, PI, PD and PID. The PID control and its innovation have so many applications and commonly used in the industry, and we hope we have been able to gain more knowledge about PID controller. Thank you.